So today, what we're going to do is some enrichment. We're going to study a thing called matrices and Markov chains. Now, matrices are something that were predominantly years ago left to mathematicians, right? With the advent of computers, we are now able to make massive consequential computations for future probabilities. Okay, but first we need to study the concept of matrices. So with matrices, right, it's very difficult to go through a newspaper, sports site, governmental site, Wikipedia, anything, and not find examples of matrices. So here's your first example of a matrix, matrice. Now, the singular of matrice is matrix, and matrice means two or more. So your first example is dealing with a football league table. So we play football in Canada, all right? And we have different teams. We're a very small football team, but the football teams are Toronto, Ottawa, and Winnipeg. These are the major teams. Now, each of the teams has information that deal with their games, wins, losses, ties, field goal points, and various other things within their team in order for us to rank them, right? So what you see here is a matrix is just an aggregation of data for which we have identified what each column will represent and what each row will belong to. Okay? So now let's formally define a matrix. So a matrix, plural matrices, is a rectangular array of numbers arranged in rows horizontally and columns vertically. Each number appearing in the array is said to be an element. So just write that down, that we have for a matrix, we have this definition, and for an element, we have that. Now, thanks to Khan Academy, you were introduced to the concept of rows and columns, i.e. the dimensions of a matrix. So a matrix, an m by n matrix read as m by n, is a matrix with m rows and n columns. So here's an example of a matrix. So this is a matrix with, this is a 3 by 2 matrix. Now, often it's very important to be able to identify elements in a matrix. All right. So if I was looking to identify an element in the matrix, the AI, let's say I have the AI of J for the big matrix A. All right. So AIJ represents an element of matrix A, big matrix A, that I set up right here, right? And at position where our position is I, which is its row number, and J, which is its column number. So for example, if I wanted to know what A23 was in my matrix, I would say A23 is the number 6. A12 is the number 3. Nope, not the number 3, but the number 2 in my original matrix above. So now let's do some mathematical operations as this stuff. Mathematical ops. So here's what you need to know. With our first mathematical operation that we can do with a matrix, we can multiply, we can add matrices. Okay, so I'm going to give you a nice little textbook definition I found. So if A and B are two matrices, right, with the same dimensions, then we define their sum, A plus B, as the matrix obtained by adding those two, by adding the corresponding elements. So here is an example of what I mean. So imagine I have these two matrices, and let's say imagine we thought that this was the A matrix and this was the B matrix that we defined. Then what we're going to look for is the result of A plus B, which is the sum. Okay, now in order to get the sum, essentially what we're doing is we need to make a matrix that's exactly the same dimensions as what we had before. But here's what we do. In order to get this spot on our matrix, we have to go and take 1 plus 3 to give us 4. Then 2. Then I usually go down. So I'm going to go 2 plus 7 gives us 9 for our second position. And then we do the same again for 3. 3 plus 1 in its matching column and row is given as, well, 3 plus 1 is 4, and so on. And that's it. That's what we mean by adding matrices. Now, that's our first operation with matrices. We can add and we can also subtract them. Now, the next thing that we have to recognize is that we can also do scalar multiplication on matrices. So let's talk about scalar multiplication. When we're talking about scalar multiplication, that's the operation of multiplying a matrix by a scalar, just a real number, and the result is obtained by just multiplying each of the elements by that matrix scalar. So imagine if I have the following. Now imagine if I had a matrix that was, I'll call this A. And with our matrix, this time we have 2 rows. It's a 2 by 3 matrix where we're going to multiply the front of our matrix. We're going to multiply our matrix by 3. So that means 3 times everything in the matrix. So what we end up having is, well, 3 times 1 for our first coordinate is 3. 3 times 2, 3 times 4 is 12. And then we can continue. 6, and then 15, and then 9, and then 18. And we're done. That's literally it. There's nothing more to it. Now, the next stage would be to actually combine those two things. So let's go and see what would happen when we combine the multiplication of scalars into our matrices and addition. Now you'll notice with the scalars can be applied to any matrix, but when we're adding matrices, we always have to make sure that our matrices have the same dimensions. But with scalars, you don't care. All right, you don't care about their dimensions. You just multiply everything inside. So let's say that we have this problem. Let's say that I want you to add or subtract this matrix. So let's say I have this matrix 1, 2, 3, 4 plus, let's say 4 times -1, 2, 6, 3. So here's what you have to do. It's just like bedmiss. When we did bedmiss, if we had a number that was multiplied into something, we had to simplify that first, then add. So here's what we'll come up with. So our first value of 1, 2, 3, 4 stays the same for our matrix. But the second matrix, we have to apply the scalar first. So now we've got -4, -8, 24, and 12. Now, to get the result, we add each of the corresponding positions in the matrix. So 1 plus -4 gives us -3, and then 2 plus 24 is 26, and then 3 plus -8 is -5, and then 4 plus 12 gives us 16. And there is our final answer. Okay, so now I'm going to give you some questions that I want you to do from a textbook that I've had for many years.